Yeah, rock and roll.
Good morning. Roman Muryns, we've been working with the lighting group and AHH for, I don't know, since 2017, the first lecture when we talked about infrared. And now it's years and years later, we've come to the stage where we've introduced it. We understand a bit more of it. And then in the last 2 years we've been doing data samples across the world using meters, etc., just to try and find what the sun is doing and confirm to ourselves that the meters are doing what they're designed to do. So what we'll do today is I'll talk with you what happens when the sun shines and how you measure it, because it changes in the course of the day, and then talk about what you might do with the knowledge, and then we'll have a demonstration of a tool I've got that allows you to map sunlight strengths or sunlight light or basking light, whether it's in a vivarium or it's been pushed out by lamp. First of all, I'll flash my big board out there. And this is really an important thing to try and understand what sunlight...
Do you want to hold the ball for you, Ron?
No, okay, thank you very much.
But sorry. I see you've got the ball.
There's other people handling my ball. No, look, this is the sun. Okay, so it comes up in the morning, and if you imagine this is a square metre, and the sun is calibrated for the standard that we talk about at about a kilowatt of power per square metre. So if you've got solar panels, and a solar panel is a square metre, there's a ratio of transfer of about 25%, you'd get 250 watts out of a solar panel. Okay? So it's real power that we're talking about. So that's a square metre with a kilowatt of power that hits the earth wherever we are, providing it's square like that. But when it comes up in the morning, that same power, that square, is look what's happened to it. The same power is now shared over a bigger area, so the power is less. And as the sun comes round, so the power received increases. So the first message I want to give you is that the sunlight strength changes in the course of the day. We know this, it's all bloody obvious, but we know it. But we don't necessarily recommend it. Don't go out in the sun at midday because it's too flipping hot. Well, that's why. But there's another thing. You see, it doesn't happen evenly. Because that same power, where you saw it happening like this, and it's kind of linearly weakens as it goes further away, when you do it on here, it's even worse. So when the sun first comes up, that glow you see in the sky isn't the sunlight, it's the diffusion of the light in the clouds above that's bouncing back. Now, on top of the fact that we've got the power increasing as the sun goes down, we've got atmosphere around here, and it's several kilometres thick. So the atmosphere at this point, where it's weakest, the atmosphere is also the thickest. So the light has to go through more crap. It's water, it's CO2, it's all sorts of dust. All of that absorbs light. So not only is the strength affected, but the wavelengths that get through to the point here change with the position of the sun. Is it so red sky in the morning, red sky at night? That's because at the low angles, the atmosphere is blocking the blue light. Okay, so not only is it getting weaker when it's low, either way, but also the wavelengths change, yeah? That makes sense? I know it's obvious, but until it's pointed out, oh yeah, that's what it is. So I've done that bit. This is the meter that we're recommending. It's a meter that's used for measuring power for solar panels. And solar panels are produced and calibrated for a specific point of the sun angle, so that wherever you are in the world, if the sun is at that angle, the solar panel will produce the same voltage. Okay, so it makes sense to calibrate the meter to go with that same angle. So this meter is calibrated for the sun being at 42 degrees above the horizon, the sea level. And there's variations of this. They're all the same meter produced with different coats on. Just like, yes sir?
Would you need to recalibrate for different parts of the Earth then,
No.
depending on where
No,
it is?
no.
And it works out?
42 degrees is the same wherever you are, providing the atmosphere is the same, and you're at sea level. It's the same. And it's weird, but you think about it, it just happens at different times of the day. In Australia it happens earlier, and in Norway it might not ever happen. So, the other thing is how you measure it, because there's different ways, conventions if you like, of how you define the sunlight sense. You could say D&I, which is direct normal, but that's just measuring the radiation from the sun itself. But we know that there's light diffusion either side. And so there's also power that gets the other side of the shadow, if you like. So what we are using, what our convention is, and the models that we use, is GNI, which is global irradiation. And that's by pointing the thing at the sun, just like you do with the UV meter, and measuring that. But be aware, because some weather stations talk about measuring it horizontally. The one in Marwell Zoo measures UVI and light horizontally, and then correlates to the cosine wave. So be careful about that. If you're taking external measurements, use GNI, which is what we're doing. Okay, here's your answer, mate. As the sunlight comes up with 1 degree, this is, I take it you're all familiar with spectrum of light, yeah? So this is UVB light, this end, and as the wavelengths get longer, this is visible light, and this is infrared. These dips are attenuation of sunlight by dust particles of water and CO2 and other crap, yeah? So what we've got is, as the sun comes up, it's very weak, but there's already some infrared content, and as it goes up higher to 5 degrees, and that's really early in the morning, the infrared content is there, no visible light, virtually no UV. And then as you go higher, it jumps up really quickly, because of that, you know, as it goes up, I showed you how it goes up. Well, at that point the cosine curve starts coming in, and all of a sudden you get big jump, and our calibration is at 42 degrees. It's not quite at the top, so if it goes past, it'll get hotter than we're measuring. And the meter is calibrated to, the sensor is calibrated around here, and it extrapolates for these values. So as you move away from the calibration point, there are some minor adjustments and errors that we have to make, and we're sort of working together to provide the recommendation that we do. So, oh, the sun's come out, but it's not clear sun. So we could have done a reading, but we did read these otherwise. And when you do your readings, you measure, and I've done a reading at home at 11 o'clock. So the reading that I took at home, when the sun was shining and I could rely on it, and these are the readings I got. Well, let's go back to this. This tool, and that will be available to you if you want to take a download or get a copy. If you go onto there, now I have to stop this. That'll get you into there, okay? That link gets you into Sun Earth Tools. And you type in Tamworth, England, and you get this, and that's a picture of the town, and we are just a little bit further down, okay? So now, as we where's the mousey, there we go. As we scroll down, I've put in year, month, whether it's daylight saving time, hour, 11 o'clock, etc., etc. So you tell it exactly where you are, you tell it where you are and when you are, and it comes up, it comes up with this curve, and I'm sorry it's washed out, not a brilliant thingy, but no excuses. This dot here tells you where you are, and it'll tell you that we're about, it says 33 degrees, 35 degrees. So now we know what angle the sun is. And you could do that for anywhere in the world. I've got tons of data from South Australia. And so when the data comes in, or you can go to iNaturalist. So if iNaturalist gives you a set of data of this little snake was out in this weather at this time of day on this month, you can work out what the sun was doing, okay? Because I had an argument with someone about corn snakes, and he said, look, they're out in January at 3 o'clock in the afternoon, and it's no sunlight and not very warm. I looked at that, plugged it into here, and found out what the sun was doing, and then I could trace what UVI was doing, and actually how much UV the snake was getting, even though it's winter. Okay, so we've done that, and the readings here will tell you the angle, the location, etc. And this is the curve for where we are now in the winter, so you can tell that the sun never really gets above 15 degrees peak of the day, and in the summer peak it'll get into 60 degrees. But the other thing that you get to see is when it comes up here, the area that it covers is greater. So not only is the sun a bit warmer, but the duration, and this is a really important thing, is the duration is longer. So if you've got a system that has the ability to modify lighting, ramp up the lamp, decay it at the end of the day, and if you had this information, you could plan the design of the ramp up and ramp down based on the curve for the animal that you're monitoring, and you could do it seasonally. Yeah? Everybody happy and everybody awake still? Yay!
Is this predictive data, or is this live data updated?
It's not live data, it's just the physics of the Earth. You know, that's how it is. You know, it changes every 10,000 years a bit, magnetic, but you know what? Next 10 years it's going to be the same.
So I might be jumping ahead, but how are we getting the watts per metre squared?
You're jumping ahead.
Sorry.
Just hang on to your pantyhose there.
Well,
Look.
sorry, there's a question back.
I do just have one quick one. You might go ahead, so sorry, Rob. If we're obviously projecting that we can ramp up, ramp down our lighting based on this, and then obviously if we can evaluate the lux in comparison to the UVI and stuff and adjust on that, that's great. But do you think there's going to be a consequence of sort of wind, air, different barometric pressure that we can't replicate that's going to make the reptiles not necessarily come out when we want them to come out, even though we're basing it on light, not necessarily environmental change?
Yes, I agree.
Are we going to, sorry.
Well, all we're doing is predicting the sun, we're not predicting the local environment.
Yeah.
When Thomas did his Western Australia thing,
Yeah.
he chose one area, 3 distinct environments. The sun didn't change,
No, I
the
understand
environments
that,
did.
yeah.
And so when your starting point is get your energy source sorted, your light source, and then develop the environment to replicate how that sun is managed when it gets to hit the dirt. And it might be more water, it might be more leaves, might be substory, it might be rocks and sand. And each of those materials will change the thermal image, the thermal behaviour locally. And if it's a small bloody box, then throw it away, you need volume.
No, I understand. No,
Yeah?
That's fine. Yeah, that's fine.
So now I need to find where, is that the, oh no, I don't know what will give me.
So 5
No, I've got to find a mouse and I don't want that. There we go. So we go back to here. And we go back to here. Oh yes, we're rocking. So we've done that. Now you asked a question just now. How do you convert it to real world? Well, because we've done these readings, like hundreds of them, I'll pick 50 for the purposes of this discussion. And what we've got here is UVI. Of all the readings I've got, we mapped them to angles, where they were taken, and then I know a UVI reading at that angle that it was taken. And when you plot that, that's the graph you get. So now all of a sudden, if we know that we were at 30 degrees, okay, or 30, whatever I said it was, 35 degrees, if we look at here, we look at that, that's about 2, under 3. So we're looking between whatever that is, say 2.5. Yeah? Look, the oval, I've got 2.6. So you can see that there's a correlation between the real world bleedings and what we're getting. So now, knowing the angles, you can use this data to predict what you could put in the viv. But that's not the whole story. Just because it gets to be there doesn't mean you have to provide it in your viv. Because just in case, I put this in case we had sunshine. Of course, just after we started, we got sunshine. Shit happens, doesn't it? So the other thing that Quentin has done, and this is based on a solar model, global irradiance, normal, SMARTS model, which is a simple model of stuff up there. I had to change the computer because the table's so big. It just processes it and run. But anyway, Quentin's gone into that. He's done a brilliant job. And what he's done is map for every degree the curve that the sun takes, but he's also broken down the wavelengths into the power at those angles. So here at 35 degrees, the power should be between 947 and 1015. Yeah?
Watts per metre squared.
Sorry?
Watts per metre squared.
Watts per metre squared. This is always less than that. And what was I getting? 1004. So that stacks up. But it's also not far from the 42 degrees calibration. So, we're comfortable. It just happens to be that the 42 degrees is kind of a common calibration when our animals are out basking. So, it kind of all fits. So they're the diagrams. And we had these loads of people. We had Minneapolis. We went to Texas, didn't we, Fran, and did loads of readings. I went to New Orleans and did readings there. We've got Serena in Europe and Jonathan in Europe. We have Dave Kirshner in Australia. Jonathan also had people in South Australia. So we've got just hundreds of data points. We haven't analysed them yet because not only have we got data points, but we've got data points of what the animals were basking, whether in the sunlight, were they passive basking, active basking, all that's got to be analysed. It's a little curve of what we've got. It's not perfect. It's not perfect because these values, because Fran and I and Serena have taken loads of readings in Europe, they're slightly biased towards Europe values, and where we are, loads of clouds, loads of moisture, so that will take, we have to take the statistics into consideration of where the measurements were taken. But overall, the curves look like that, which is what we would expect, and so that as the sun goes up higher, the proportion of infrared to visible light changes, and there's the proportion goes in favour of visible light. We know it does that, we know it gets stronger and brighter as the sun gets higher. So the next one is, when we did the UV, when we did all of these charts, we revisited every single perception we had. Is it the right colour scheme? Are we describing it properly? How do we present it? We've gone through that, and we spent weeks, didn't we, Fran, just going backwards and forwards. No, I don't like that colour. This is a better colour. Can you see it if you're colour blind? All those sorts of questions are put on the table. What we've ended up, say, for I'll press the wrong button. What we ended up with is this curve, and then I said, well, 2006 or whatever, we started doing the Ferguson zones, And what do they look like? So do these curves that I've got map the curves that Fran and Gary Ferguson did all those years ago? And you know what? I didn't expect it, but they do. They do. They bloody do. So what I did was I mapped the colours on these bars where the Ferguson zones fit. So where the corn snake was, the shade values put under one UV when they're out, and they're there. But there's no hard rules. You can go to Florida and see corn snakes at 10 o'clock in the morning in February, and you go back to the chart, you'll find the UVI is 3. So, and that fits in with there. Now, by accident, this is the chart that's on produced by the people that make the solar power meter, the solar meter. And you've got Dan there and Fran that were the authors of the paper. And so the people that have contributed to this one way or another is that Francis and me and Quentin started this off in terms of rewording it. Serena has been in the background and she's made comments and added. So the people that have contributed it, then we go on to, Fran was the lighting expert for Piazza for years until she retired. Serena is the lighting expert for DTHT, the German Society. When Fran retired, Tom took over as a lighting expert. Dan Garrick's in there, and Ethan, who's the other fellow that will be talking to us, works for Dan. So the people that started this off are still in the flipping loop. And so it's just developed and grown. So that's where we are. I always like to double check with it. It's really important that we do that. So we took the worst case place. This is winter solstice, as low as the sun gets. And what we planned is, this is the forecast model, the SMARTS model, and these are the readings we get. Now, Jonathan's in Vienna, he took readings, and they were way out. What Quentin did was looked at the meteorological, because it's local meteorological forecasts, and these are the mountains, and there's funny ozone stuff going. Now, the interesting thing is the local model showed an increase, but so did the meter. So, you know, it gives us confidence that what we're doing is about right. Now, this is Fran in 2012, showing us how she's measuring and mapping out right. This is a 2006 chart that she's done. It's a wonder. How long did it take you to do, Fran?
I've no idea.
But this is what started it. This is how the Ferguson zones were mapped against this. You know, all that work. The thing is, there was only a couple of lamps in those days. Now there's flipping millions of them. They're coming out of China like there were peas coming out of a pig factory. So what do you do? We looked about how do we automate it. And when we first started, I had the idea of doing it this way. And then we had internal stuff and then did it another way. But coming back, knowing that we've got, I wanted everybody to be capable of doing this. It should be available freely to everybody in a common place with access by everybody to that same common place. So we revisited everything, the colours, and Fran changed some of the colours, just one or two did you at the end. I think I changed the purple, you changed the greens. Between us, we came up with this colour, and it looks crap on there, and there's a better variation done by the labs. So the tool that we've got here, that will be demonstrated by Tom and Ethan later, shows these it's the same data as before, but you could do this in a big one like that probably take half an hour, but a short one, 15 minutes you can do it. So that's the UV one with the scaling, and the tool itself is just a spreadsheet, but it's got instructions on how to do it, the pitfalls, how to measure, etc., etc. Same thing for infrared, the near infrared, and we're not talking infrared A, because the meter doesn't measure infrared A, it measures near infrared. It measures everything from where interest starts, 700, and it measures some more to 1100 and predicts the rest, but the value it gives is near infrared. And the lamps don't produce just infrared A, they produce near infrared. And the sunlight doesn't just produce near infrared A, it produces near infrared. So we're measuring near infrared. So we want to drift towards calling that set of wavelengths, so it's UVB, visible light, and near infrared. And because of the testing I've done, the papers written by other people, which I refer to in my notes, and because the meter is not designed for measuring lamps, it's designed for measuring sunlight, which is brilliant at doing, there are issues with tungsten halogen lamps where they produce light where there's water filtering. They produce light, visible light, which adds to energy density, and we're not necessarily interested in that component. So we have to recalibrate the value that we read on the meter for the context that we're using it when we look at infrared lamps. Okay, so having taken all of those things into consideration, we put qualifiers of what levels of infrared are appropriate to different zones, because they are, as you inferred, sort of dependent on where you are, and they work pretty well. We did the same thing for visible light, the same tool in the same positions, just you change meters will give you visible light. And again, we've looked at how strong the light should be, bearing in mind we can never reproduce sunlight, 120,000 lux. To produce that, you're going to have to use a lamp that's 5 times more powerful because of the efficiency of lights. But, flipping heck. But these values work. They work practically because I've tried them. They work practically because other people have tried them. So we're now defining the values that we might have achievable for the use of visible light. Okay? Still awake? Still with us?
Yeah.
Yeah. So I talked with James Hennessy at the London Zoo in Ireland, and he said, that's interesting, I'd like to try that. And he did. And so he's got these alligators, and you might have seen these on the web somewhere, and he put in the values that we talked about. And he's using that, it's not a white infrared, it's a reddish tuned infrared, there's 4 of them, and you can just see the hue, and they're loving it. James is just gobsmacked with how effective that is. Okay, and so after COVID, we had an AGM at Chester Zoo. I asked Sharado, can I go and check the Komodo dragons? And I bless the lady, I think the name was AJ, J.A. She had neat handwriting, because if I'd have written it, I wouldn't have understood it. But she took the readings, and she put 230 watts per square metre for the favourite spot for the Komodos, the basking. And if you look at 230 watts there, this level is the upper medium level for tropical and upper temperate climate animals. Smack bang in there. Fantastic. And those were at 280 to 320, so they're a bit higher. But the point is, those values work. It means, one thing that the others in the team insisted on is, when it's too high, we make it red. That was the starting point. No matter what I said, it's got to be red. It's got to be red. So it's red. And if it's there, they don't bask. They just go away. It's too hot for them. So,
Is the assumption that the animals are detecting the heat density then, as opposed to the light strength or
no,
something?
not an assumption.
That's
They're doing both. They get the cues through the eyes at, you know, the 480 nanometers to the ganglion cells with the bright white light. That tells them, hey, it's daylight. And then they get the subcutaneous stuff through the infrared that warms them up. But you can't separate them. You can't give them that without proper cues of where to go and bask. Because the sun doesn't do that. You know, it's interlinked. Except
Just when you have time, we're about halfway through, just so you know.
okay, thank you. Except that, shit, I forgot what I'm saying.
Can't separate.
Yeah, because they will take the warmth, they feel the warmth, that's what they come out first thing in the morning. Right, Tom Wells, Ethan Parrott will now continue with the demo. Your timing was spot on there.
So, I was just going to say one quick thing. With the power meters on that Sun Earth website, in theory, if I'm reading it right, if say you've been out in the field and you've taken some UVI readings in full sun, irrespective of what the clouds are doing, but as in like not partially shaded or whatever, you could then, if you know where you did that, you could then go onto that and see what the power density was doing without the meter. You could sort of do it
You can guess it.
after the fact kind of thing. Because then in that case, then when we're doing power density readings, assuming that we have confidence in the reading, in the reader, the only thing we'd actually ever need to do is do it when it's dapple shaded or partially shaded or whatever to see what it's actually
The
doing.
local
because the
environment
website could tell you.
will,
the rest.
and the shorter the wavelength, the more it's screwed up by local environments. UV bounces around all over the place because it's a shorter wavelength, and you'll get UV readings in the shade. But if you stand in the sunlight and you go in the shade, you get cold immediately. Even though, so the stronger the sunlight, it's a good indicator, but you go in the shadows, you'll still get some because of the diffusion effects. Okay, so I'll set this up for you guys. No, that's not it.
And I've got what to do works for. I can literally go back and after the fact figure out what.
So we're going to do this one. This is. Oh, yeah. This is what the tool looks like. I'll get you onto. I'll get you onto there. Get you onto there.
There's nothing so far as you can do, but different stuff.
Okay. Well, yours, guys.
So yeah, this is our first run of this. Hopefully it works out all right. But we've got lamps at the back so that we can show everybody afterwards. But we sort of figure if we are running out of time, then we'll go through this first, and they'll be there for the afternoon. So if people want to come and have a look at those and ask about them, they can. So basically, what we were doing with these larger lamps is a scaled up version of what Rom did with us and created and sort of showed us, and we kind of practiced it on some of the bigger lamps that you can use for zoo enclosures or for larger species and should be using. So I guess in the same way that with the UVI readings and the irradiance charts that Francis was doing with the UV lamps, and you can see that not all lamps are the same, they've got significantly different spreads. You get the same issue with no 50 watt halogen is identical, no 1.3 kilowatt patio heater is identical. So this irradiance mapping, which we're going to demonstrate, and I guess one of us will, do you want to type or
Yeah, go on.
So this allows us to map what the actual spread of the lamps is doing, so you can choose the appropriate lamps for the... did I knock something?
Yeah. Hit it. Talk to it. Yeah.
There we go. So we did this... Working now. You can see it there. So this is the sort of thing, I suppose, that's probably relatively easy, that other people can create similar things and most people can probably do that in their own household setting. So this is something that if you've got solar meter, lux meters, power density meters, you can do this charting yourself. And then if you've got a much larger space, you can do it for things like light waves, which are commonly used in zoos. If anybody went on the zoo tour yesterday, you would have seen quite a lot of light waves in the enclosures, some of the high bay LEDs that are often used in warehouses, but you can use for providing lighting in much larger enclosures or for big species. Or we've got a lamp that was custom made for Marwell.
Custom chip, yeah.
A custom chip that was done for Marwell for heating and or for lighting some of the bigger enclosures, and it's basically just a scaled up jungle dawn. But yeah, I guess we start the mapping.
I think something to note as well, if you're doing this yourself, is obviously this is set out into, what is it, 5 centimetre increments?
Yeah.
But if you're doing something on a larger scale, what we found is you end up taking hundreds of readings and it can take a really long time. So it's worth sort of using a bit of common sense, and I guess we could probably, like for the larger things, you can do 30 or 40 centimetre increments. And what Rom has cleverly inputted into the spreadsheet is a little scaling factor in the top corner. So say as it is 5 centimetres, if you wanted to change it to like 10 centimetres, then you put a scaling factor of 2, is that correct?
Yeah.
And then that would adjust itself automatically, so it should be fairly user friendly. And I think it's also quite interesting what we found is, like with the infrared heater we've got at the back there, you might have two that look identical on the outside, right? So that's a tan sun Algarve, and we also had a Knightsbridge, and on paper they should perform exactly the same, but we found like almost a 50% difference in the power output from the two different lamps. So I think particularly for like zoo licensing and that sort of thing, if we can produce these graphs and demonstrate visually the impact that they're having, then it's a lot easier to sort of make a case for why we're doing what we're doing.
We've got some of the posters printed on the wall, so we've done one of those charts is that Tansal Algarve we've got, and then we've also got a chart for it. I think it was a higher wattage, I think a 1.5 kilowatt Tansun Heliosa, and the actual spread of the lamps is significantly different. So that's punching sort of I think about 300 watts per meter squared down to 2 meters, whereas the Tansun was kind of giving you levels about a meter away. But yeah, so if we start recording. And then hopefully this makes sense. And this is, So starting down the middle line. So I'm moving it down because at the moment it's giving too high a reading, so it's not going to give it. So I'm just going to move that back until you get your first reading. So 15 centimeters away, 1680, 20, 937, 25. 613, 30, 428, 323, 244, 193, 159. Go back up to
Tom, with this, have you found, because these are obviously snapshots in time, are you also doing them over duration of bulb length and then mapping the generation? Because I imagine some of them with a really high output initial, you're going to see a steeper decline, whereas maybe some of the lower initial might have a greater longevity then.
for the light waves, I suppose the UV tubes definitely degrade over time.
I wonder if it's the same with the infrared then.
The infrared, we haven't mapped them over time. I don't know if you
That's the value of this. It's so quick to do. You can do quick spot checks. You could map that very quickly, because this will do. We've got 5 minutes bloody warning that woman over there. She's gone. But you can do this so quickly, and because if you've got a grid and you know the spot check at the point, you don't have to do it all. You just put the meter in there. You've printed this out as a PDF, so you've got that on a piece of paper, and you could do it just like you measure other parameters in your zoo. You can do it every 6 months and say, I'll check at this point, I've got the data point already, it's as a PDF, and you can see the decay in power. But tungsten halogen don't seem to do that.
Because for seasonal variation in some species it'd be useful, because actually if you knew what your decline was, And you could then, because one of the problems I have is for some of my species, every 3 months I'm changing wattage bulbs to get different heats if I don't want to use thermostats and things.
No,
So if you had a bulb that you knew it had a decline of power output across a year, actually it'd make your life a lot easier.
You have bulbs with 2 different powers. It's April, I'll go from this bulb to this bulb. It's infrared, it tends to be more stable. It's not like UV and not like light. It's a more stable value, so you can do that. And the other thing is that is more effective. It's not only you can change the type, but you should be changing your timescales. It's the diurnal cycle time is what matters, and that's the thermal. It's the integral of power you're going over time. So the shorter the time, the lower the value. It's that heat build up. So you've got to do them both. You've got to put time as well as power. Because that's what the curves tell us.
You could always have as well sort of multiple, so instead of having one lamp to produce the desired power density that you're looking for, you could have 2 lamps and then switch one of them off.
Yeah, absolutely.
And sort of saves you swapping bulbs out.
Yeah, that's something we do.
Have those 2 lamps on different time cycles.
Yeah.
I've got a couple of questions. With the scaling, why would you go bigger or not smaller? Well, say you've got 5 centimetres.
Yeah.
Why would you go bigger or smaller with the grid?
So I think, for instance, with the light wave that we did at the back there, we were measuring that, I think, at scaling of 20 centimetres, I think.
Yeah, you sort of get loads and loads of repeat readings. Really.
Sorry, it's larger or smaller?
It should say down the side.
Yeah, so like with like the light wave, for example, where it can punch so far, if you're doing every 5 centimetres, you're getting like 0.1 of a difference or even less between each reading. And I don't think that's really necessary for the sake of...
Yeah, so you do the measurement, you change the scaling, you don't have to take more measurements, you just change the scaling.
Confusing me is the scaling factor. So that's 5 centimetres and you put 2 in.
Yeah, it'll go to 10.
What are you doing there? What are you
We
doing?
can record, so if we wanted to only record every 10, if this was a much more powerful lamp, for instance, and to do it for every 5 centimetres, you might be doing 3 metres of readings.
5 centimetres 2, how are you getting that?
So to change that scaling factor, that will give you readings down the side.
What's the scaling factor?
It's not letting me click on it.
Ah.
Is it locked?
So with the scaling factor, if you've got that set to 1 at the moment, the centimetres underneath it is
Okay, that's a
5,
scaling factor. Can you see the scaling factor there?
I see it.
Okay.
I'm wondering how you decide that 5 centimetres is that.
So we know that this is 2 centimetres for the block. Yeah, so we want it to be 5, do you?
That's what we're doing.
Okay, so what we do is we go 2.2.5.
Yeah, I'm still not getting it.
Sorry,
Sorry, I'm not getting why. 5 centimetres is 2.5. What's the conversion here?
2.5.
So these are I think if I'm getting what you're asking, so these are 5 centimetres measured. The scaling factor just affects the measurement on the chart. You choose how you want to measure it. So if you had a bigger, more powerful lamp and you didn't want to measure every 5 centimetres, you measure every 10 centimetres and then you can adjust the chart so that you have 10
right,
centimetres.
so you can sort of bring it up and down and on the software.
So that just changes what the measurement would be down the side, and then you take those measurements where you want based on the lamps you're
Quick interject, what it might be easy to do to add is do 5 centimetres scaling factor X, 10 centimetres scaling factor X, so people don't have to work out the maths for the
I'll make a note of that, that's a good idea, thank you.
Roman, instead of scaling factor, you could have grid size as input in your sheet.
Well, I must admit that it's a bit confusing for me, but I'll get it.
So the scaling factor, so if it's 1, it's 1 times, so that's originally set to 5 centimetres. That scaling factor of 1 is 1 times 5 centimetres.
Right, yeah,
So
right.
If you change it to 2, it's 2 times
Yeah,
5,
no,
and
you know.
then you've got 10.
Like if I put 2, and then it changes it to 10, 20, 30, 40 on there.
And then we just measure at those increments depending on the size of the lamp. And
Yeah, no, I'm with you now. Yeah,
Can I just ask, this might be a really dumb question, but it's something I get asked about a lot. With the red light, is that damaging to reptiles' eyes? Because it's something that I'm always, I know there's a lot of different opinions about it.
And in terms of leaving it on all the time, I mean, they
Like
can
a lot of
see
people
red.
use it for nighttime, as like a nighttime heat source.
So they're able to see
Right.
red light, or
Yeah.
many species of reptiles and amphibians can. So I suppose whether it's damaging to the retina, I don't believe it is. But it would mean that it's not dark all the time for them. So at
Yeah,
night,
yeah. So
they're
is it
still.
more beneficial to have like a ceramic heat lamp over?
I mean, I suppose so. In nature, you'd have the sun would produce infrared, a near-infrared wavelength,
Yeah.
which would then warm the surfaces. At night, those surfaces would re-radiate that infrared as longer wavelengths.
Yeah.
So, yeah, I suppose, I mean, a ceramic lamp or a heat mat would produce longer wavelength infrared, and
Yeah.
it sort of depends on your enclosure and what you're trying to do.
So
And
is
if
it
you
better-
insulate the
yeah.
space, if you insulate the enclosure so it holds heat better at night,
Yeah.
that would also mean that
I think, I'm sorry, Tom. I think the issue is, are you talking about a light for basking?
No, that's what I was going to say is.
But you're now talking about a source of heat for keeping the rest
So
of
just
the area warm.
What I see a lot of people doing is using an infrared light as a night light, as such,
No,
so
it's
they
not
can still.
appropriate.
Yeah, that's what I thought. Yeah.
No,
So
it
you're
should be
using
a
that
black
alongside
source.
a basket
It should be a
light.
black source for
Yeah,
nighttime
yeah.
heating. Or else
Okay.
you're screwing up the diurnal cycle.
That's what I thought. Yeah, no, I just wanted to. Cool. Thank you.
I think we're going to be getting our plug pulled at the moment. I hope this was interesting. Please come back with more questions.
Very interesting.
There is a thing actually. How you spread? You've done vertical, is it? How are you getting spread? How would the pack?
So if we carried on, you can move this out there.
Right. That's what they're saying.
What you could
And
do
measure it
is
to
we
10 centimetres
could
across,
show you on
10
this graph.
centimetres down. And if you have a look at the
Go and
posters
have a look at the
there.
graph. That shows you what the spread is.
Oh yeah, I just put it out. Make it easy.
Oh
I see the angles change now.
Yeah. Because you're always pointing.
We did that with one of the nights.
Well, we did two planes. We did horizontal like that way and that way.
He's doing it.
But we haven't yet done any sort of bird's eye view. But it is something you could do, and that's something you were talking about earlier.
Yeah.
If you were mapping like your blast zone within an enclosure, then that's how you would do it, and you would get an idea of the spread on a sort of a flat surface.
Because for most, we're not keeping the lights at the back of a surface,
exactly.
they're centralised,
Yeah.
so it would make sense to
You
see.
could scale it to a blast zone, couldn't you? If your blasting spot was 60 centimetres, you could work out the scale to 60
Yeah, absolutely. Yeah. See that mesh there?
Yeah.
Pick it up. You're part of the show now. You see, you put your meter on the mesh, and you've got the two numbers. The numbers the same as on here, the same as on the chart. You take your reading in the mesh, put it on the chart, and then you work out how big the mesh is, scale it, and your answer's done. Now that should be used for research because no, we're done.
Back.
Sorry.
So I'll drop you back. 2 minutes, everyone else is finished, and I'm just waiting for you now.
Well, we're done. We knew you were coming.
Oh, look you. Mwah. Okay, whenever everyone's ready, you can just flip around.
If people want to see the lamps at lunch, like we'll be about and can leave them here.
Yeah.
So,
But I have another question. If we should be really far beyond in the future, light technicians should invent adjustable bulbs which are adjustable in frequency, intensity and UV. And then you have to link them with your measurements, so then I can perfectly follow up the cycle of my chameleon person in Madagascar by doing this. But this is for the technicians, the ultimate thing, and for us it should be wonderful. Isn't it, Roman?
Your aspirations have got problems.
Oh, but I'm a dreamer.
Your aspirations have got some limits.
Practical limits.
Yes, practical physics.
Yeah, physical limits.
You cannot. Do you have a loudspeaker system at home? Hi-fi.
Yeah.
Yeah. You won't get a tweeter perform the same as a bass speaker because the tweeter is short frequency and the bass speaker is big.
Yeah.
Same with light.
Okay.
UV is short frequency, short wavelength, and then infrared is long wavelength. You will never get a tweeter producing bass.
Okay.
Yes, sir.
Probably the most important question, where do we get the spreadsheet from?
Okay. You can come and give me your email address. If you've got a memory stick,
Yeah, I don't, but...
if you've got a memory stick, I can put the presentation, the data on the memory stick for you. Come and give me your email address and I'll send you a lot.
For anyone who's not confident, Simon and I are going to
Email address. Okay, obviously. Yeah, no problem.
different lamps.
I don't want anybody owning. It's not
Makes sense. It's not.
So this problem with innovation is going to be important. And yes, the mail makes no sense somewhere.
We can talk.
As soon as you said the first bit, my brain went,
Oh yeah.
But with the flood bulbs, even if you have exactly the same brand with exactly the same wattage, because they're coated, it's all the manufacturing process.
Yeah, with the shape of the bulb, everything changes.
Doesn't give you a
That's
multiplied
why it's hard
output
to.
increase. It's such a flaw.
Yeah. Well, I suppose it's going to be like a floor.
Oh, we got only
No,
you.
it's
round two.
frustrating.
Yeah. Come on in.
I didn't actually sign up with the.
No, it doesn't matter. I don't care. I don't care. Come on in.
I bet that's a yes.
Wow, no. Because, sorry.
Second seat.
Very quick follow-up question before. So if you set it up that way, because obviously the lamps, the lamps are in circular, the spread's there, because when it's like we're talking about 3 units, the
Aha.
spread there.
Let me show you.
I just wanted to
If I can
confirm.
get round to do this. Now, so this is the test sheet.
Yeah.
So if we go for, get the mouse on. Where's my mouse gone?
There you go.
Where? Can you see it? There it is, yeah. I lost my mouse. So you can go this way.
Yeah.
And it's a sideways sheet.
Brilliant. Fantastic. Okay.
yeah, but like I say, you can definitely plot it off. Like you want to exercise part of it, or you can plot it, work out what lamp you need and what distance to create.
But I'll take your advice and I'll change it. I'll
I
add.
just think some people don't
No,
understand.
no.
I'm awful at maths, so that would help.
Yeah, yeah.
It makes sense for me.
Yeah, yeah.
Like, so rather than us picking something, which is easy if you did 10, 5, 10, 15, 20, 30, 60 centimetre X.
Yeah, yeah.
Yeah, it just makes it easy.
No, I'll do it. I'll add it.
Yeah.
That's the whole point of doing it at this stage.
No, that's really good, thank you. That's
You're welcome. And you're going to share this with our John, aren't you?
Oh, definitely. Yeah, don't you worry. Well, would it be possible to send the presentation through with the spreadsheet?
Yeah.
Thank you.
Yeah. Anything's possible.
Yes.
You having a good time?
Yeah.
And you're going to go back to America.
Yep, my flight leaves at 9 a.m.
We all good and
Full day travel.
we all good and changing around yet?
Yeah. All good, sorry.
And changing round.
Yeah.
He's new, aren't they?
We've
Just
got to do
running
a
around
meeting
checking.
this time so we can be.
People are still moving around, so
Yeah.
there's definitely at least 2 more coming in that I've just spoken to.
Okay.
At least.
Something I was going to point about that we didn't mention in the last one is I don't think we know why we're doing power density as opposed to temperature.
No, I know. But that's in the words. That's in the words. And Ben is totally up for having the notes in there. So you just enjoy with that.
Give it an introduction to it and people can go and figure it out themselves.
You can have that.
It's alright, Stuart's going to send me a bunch of coordinates and stuff, so yeah, but thank you. Cheers.
Yeah, you're welcome. But, okay.
It's right, yeah, but he was running through the whole map and giving us like little pointers and stuff, so I'll just do it on Google
You
Maps.
sure you don't want it? You can have it.
No, it's okay,
Okay.
honestly. Cheers. Alright, you doing a good set of planets? I think so, yeah. I sort of missed the first half, so I saved this one. I'm trying to photograph all of them at the same time, so.
It was chopping block the first one and the second one.
Yeah. We did, yeah.
Which one did you do before?
Kosh.
Okay. And which one did you
I was
go for?
at the bioactive one, right outside.
That was with Francis, was it? No, that was...
I don't remember his name.
You can be closer, we won't bite. That hour went so quickly, didn't it?
It went a lot quicker than I thought it would.
I thought I was doing the right half an hour, but did I take a lot longer?
No, I think you were spot on, to be fair. Like,
I
it
think-
15 minutes.
I think they started a little bit late.
Yeah.
I'm
There's
having
no
to,
way music 15 minutes.
I'm having to juggle. I swear. I might change it a little bit. I might stop the camera.